Good morning, everyone. This is lesson 1.4 from Physics 20. This lesson can be found on page 18 of the Unit 1 handout on kinematics. You have already learned how to find acceleration using a velocity time graph. A velocity time graph is a graph where velocity is measured on the vertical axis and time is measured on the horizontal axis. And we already know that the acceleration of an object can be determined by finding the slope of that particular graph. What we're going to be doing today is looking at using those types of graphs, velocity time graphs, to determine displacements. And then we're also going to calculate what we refer to as average velocity. So to begin with, as I said, you should know that the slope of a velocity time graph will give you acceleration. The reason for that, and we've talked about this before, but the reason for that is fairly straightforward. If you have a graph in which velocity, and I'll just go with uniform acceleration, you have a graph in which velocity is changing in this fashion. Let me label the axes, where this is velocity and this is time. The reason why the slope of that line is going to give you the acceleration is because acceleration is defined by the change in velocity over the change in time. And when you find the slope of a line, one of the earlier methods that you're taught is you pick 2 points on the line, you extend the 2 points to create a right angle triangle, and the height of that triangle is what we refer to as the rise, and the base of that triangle is what we refer to as the run. Well, stop and think about what the rise is. The rise is the change in the velocity. This is delta V. What is the run? Well, looking at that triangle, the run is a measurement of the x-axis or the horizontal axis, which is a change in the time. So when you take delta V, which is the rise, over delta T, which is the run, you get the slope, but delta V over delta T is by definition the acceleration. So this is nothing new. We already know that this is the case, and we've used it whether the line is straight or we're dealing with a curve. It turns out that there's a feature of velocity time graphs that can also be used not to find the acceleration, but to find the displacement. So we're going to take a look at a couple of examples, and from those two examples we're going to come up with I don't really want to call it a shortcut, but a rule that takes a lot of the thinking out of what's happening here. Let's take a look at the first example. We have a drone which is moving at 3 meters per second to the right, and it's doing this for 200 seconds. Then it makes an abrupt change in direction and moves at 3 meters per second for 50 seconds. And that information is shown on this graph. And the problem is, what is the displacement? This part of the graph seems a little suspect. Most people will look at that and go, well, I'm not quite sure how that happens. And it's what makes this graph kind of goofy to look at. This part makes sense. The drone is flying to the right at 3 meters per second for 200 seconds. It's flying to the right because the velocity is positive, and that by definition means to the right. And then all of a sudden at the 200 second mark, its velocity changes to negative 3 meters per second. And it continues traveling, but now it's moving to the left because the velocity is negative. And the keen student will question how an object ends up going at 3 meters per second to the right and then over no time interval changing to 3 meters per second to the left. And I'm going to tell you that that can't happen. But in order for us to understand more complicated scenarios, we have to start with simplified versions. So don't let the shape of this graph throw you. So how are we going to find the total displacement? Well, we can look at the top part of this graph. Up here, what we have is uniform motion. This is uniform motion. Because for that 200 seconds, the object is traveling at a constant speed in a straight line. And we can use the formula distance equals speed times time to calculate how far the object travels in that 200 seconds. So if we take 3 meters per second and we multiply that by 200 seconds, we get 600 meters. So for the first 200 seconds, the object travels 600 meters. When we take a look at the bottom portion of the graph, and the trip, or our analysis anyway, ends here at the 250 second mark. But if we look at that little piece of the trip, that is also uniform motion. It's traveling at a constant velocity or speed in a straight line. So the distance traveled here can be found by taking the speed times the time, which will give us 3 meters per second. I'm not including the direction here. I'm just talking distance equals speed times time, times 50 seconds, which gives us 150 meters. And this is what we're dealing with now. We're asked to find the total displacement. We have 600 meters travel here and 150 meters traveled there. And if this question said, how far did it travel in total? What's the total distance? What we would do is we would say, well, that's 750 meters. But it asks for displacement. And the displacement during the first part of the trip, this displacement in here is 600 meters to the right, whereas this displacement down here is 150 meters to the left. Pardon me, 150 meters to the left. So it's a simple matter of looking at those two displacements. You learned in, I think, the very first lesson, and in this case you have two options. You can take the larger of the two displacements and subtract the smaller. So 600 minus 150 is 450. That's the magnitude of the total displacement. And then since it was more to the right than it was to the left, the direction of the total displacement is to the right. What you could also do instead, and if you're at West Country Outreach, I talked to you specifically about this the other day, is assign a positive to the 600 because it's to the right, a negative to the 150 because it's to the left, and simply add them. And I like this because we're finding total displacement, so we're adding displacements. And we get positive 450 meters, and the positive means to the right. I think it's best to write the actual direction as a word. I think when you get to a final answer, it's better to write 450 meters and the word right. Now, I want to point out something to you here, that what we could have done is we could have looked at shapes. That this first part of the journey is represented by a rectangle, and the second part of the journey is represented by a rectangle. One of these rectangles is above the time axis, which means it's positive for the displacement, and one is below, which means it's negative. All you need to do, and I'm going to erase some things here so that I can repeat this whole process, all you need to do, pardon me, is don't worry about physics, worry about geometry. And ask yourself what the area of these shapes is. Well, the area of this, it's a rectangle, it's length times width. The length is 200, multiplied by the width, which is 3. That's 600, and that happens to be meters. And it's a positive displacement because it's above the x-axis, or the t-axis. If I find the area here, it's length times width, and the length is 50 seconds. The width is 3 meters per second, so we get 150 meters, but it's below the t-axis, so it represents a negative 150 meters. And I know that you're going to look at that and you're going to go, well, what's the difference? Why couldn't I just do it the other way? Well, you can. But it's easy in this case to do it the other way because we're dealing with two rectangles. We're dealing with uniform motion twice. Let's take a look at the second example. All right, example 2. From the graph shown to the right, determine the total displacement during the 10-minute trip, and also during each of the 3 parts of the trip, find the acceleration of the object. So just to talk about this graph briefly, it is a velocity time graph. There are 2 portions in which the velocity is not changing. So for the first 4 minutes, it's experiencing uniform motion. And for the last 5 minutes, it's experiencing uniform motion. But this section in between, the object is experiencing what we call uniform acceleration, or in general, non-uniform motion. Now, if you wanted to find the displacement during the first 4-minute period, it's uniform motion. You could use speed equals distance over time and find the distance. And you could do the same thing for the last 5 minutes. But you don't have a formula to determine the distance or displacement from the 4 to the 5-minute mark. So instead of relying on formulas or even having to know what type of motion is involved, we rely on what we learned in the previous example. Namely, that for a velocity time graph, if you find the area of all of the shapes, you are finding displacement. And we can break this entire graph into 4 different shapes that are all above the time axis. The fact that they are all above the time axis means that all of these displacements we get will be positive in nature, so they're all going to be east. This is a really simple question when you understand that shortcut, which is to find the area. This is a rectangle, so we can take length times width. The length is 4, and the width or the height is 6, but we have to be careful. We have to be very careful here, and this is unusual, but it happens from time to time. The time is in minutes, and we cannot multiply meters per second by minutes and get any meaningful result. So when we talk about it being 4 minutes, when we talk about the shape of this rectangle and the width of it is 4 minutes, we have to think of that in terms of seconds. And 4 times 60 is 240. So the area of this rectangle, using compatible units, is 240 seconds multiplied by 6 meters per second. What's that? 1440. You can check it on your calculator. I'll check it in a second. And that's going to be meters. This rectangle on the right is also base times height. It's a total of 5 minutes when you take a look at the length of this rectangle. It's 5 minutes. But if we multiply that by 60 seconds per minute, we get 5 times 60 is 300. So it's going to be 300 multiplied by the height, which is 2 meters per second. So I'm getting 600 meters here. If we do the same thing for the rectangle at the bottom, it's 1 minute, which is 60 seconds, multiplied by the height, which is 2 meters per second, which gives us 120 meters. This is a triangle, 1/2 times the base. The base of this triangle is 1 minute, which is 60 seconds. The height is from 2 to 4 is 4 meters per second. So we multiply that out and I get 120 meters. And now what we have to do is, well, 2 things. We want to check all of the calculations and then add up all of let's go blue. All of these blue numbers, 120 meters, 1,440 meters, 600 meters, and 120 meters. So we'll double check all the calculations, or I will. You should be doing the same. I'm just looking at the first rectangle, 240 seconds times 6 is 1,440 meters. Yep. The triangle is 1/2 the base times the height. The base is 1 minute, which is 60 seconds. So 1/2 times 60 times the height of 4 meters per second. That's 30 times 4, which is 120 meters, and that's cool. The rectangle on the right is a 5-minute length, and that happens to be 60 times 5 is 300 seconds, times the height is 2 meters per second. I'm getting 600, that's okay. And the bottom one is 60 seconds by 2 minutes, or 2 meters per second, which is 120. So we add all these together. We got 1,440 plus 120 plus 600 plus the 120. Just want to double check now because I got 120 twice, but that's okay, that's correct. And we're adding all of these together to get 2,280 meters. The reason why we're adding them together is they are all positive displacements. So the answer to the first part of the question is 2,280 meters. Total displacement, 2,280 meters. If we take a look at the graph, all of those velocities were east, so that means all of these displacements are east. We can put east as a direction. Now we're also asked to determine the acceleration of the object during each of the 3 parts of the trip. I will leave it to you, and if you need to pause the video at this point and think about this, do so, but I will leave it to you to give some thought as to why the acceleration during the first 4 minutes is 0 meters per second squared, and during the last 5 minutes is 0 meters per second squared. You should be able to figure out why that's the case. For the center section, we can use the formula that we talk about in the other lessons. Acceleration is change in velocity over time, which I prefer to just write VF minus VI over T. So VF refers to, I'll just do a bit of highlighting here for you. VF refers to the final point in time at the end of that middle interval, whereas VI refers to this point. So we have to take the velocity at the purple point minus the velocity at the yellow point divided by the total time, which is 60 seconds. Let's see what happens here. VF is 2 meters per second. VI is 6 meters per second. And T is 60 seconds. So I end up with the acceleration is equal to -4 meters per second over 60 seconds. 4 divided by 60 is 1 over 15, which apparently is 0.067. And it's negative, so the acceleration during that middle portion is negative 0.067 meters per second squared. All right, for an object whose velocity is changing, in other words, it's accelerating, you can find average velocity. And whatever you think the word average means here, just put it out of your head, because what it does not mean is what it would mean in a math class. Okay? So we're going to learn what it means and how to work with it by looking at this situation. A student jogs 750 meters east in 6 minutes. By the way, we want to always work in meters and seconds So if we take a minute here and take 6 minutes and multiply it by 60 seconds per minute, we can just make an observation that's 360 seconds. They then do static stretches, and what that means is they stand in one place for 10 minutes doing a bunch of stretches and exercises. Then they run another 2 kilometers. Well, we should put that into meters. 2 kilometers is 2,000 meters. They're still going east, and then they're going to take 11 minutes to do that last part. So 11 times 60, I believe, is 660 seconds. So I just want to take a minute here and confirm my mental math. That 6 minutes is 360 seconds, and it is. That 2 kilometers is 2,000 meters, and it is. And finally, that 11 minutes is 660 seconds. 11 times 60 is 660. We also have that 1 kilometer, which I almost missed. So we have 1 kilometer in 20 minutes. 1 kilometer is 1,000 meters. 20 minutes times 60 is 1,200 seconds, and I don't know why. I am second guessing myself with that, but I am. So I'm going to grab my calculator and just double check that. 20 times 60, yeah, of course it's 1,200. For some reason I wasn't sure. So we have all of these distances and times and directions. So what is the average speed? We have to take a very broad approach here and just say to ourselves that average speed is basically the total distance over the total time. Not basically. Average speed is total distance over total time. So we need to add, what do we have here? 750 meters plus 2,000 meters plus 1,000 meters. Boy, there's a lot of information in this question. Let me just double check here. 750 meters, we have another 2,000 meters, and we have another 1,000 meters, and we need to divide by the total time, and the total time is 360 seconds, and another 10 minutes I didn't convert, but that's 600 seconds. And then we have another 1,200 seconds. And then we have another 660 seconds. So once again, a lot of numbers. I'm just going to go through this whole thing word and number by number to make sure I got them all. 750 meters, no meters for the static stretches, 2,000 meters, 1,000 meters, and then we have 360 seconds, 600 seconds, 660 seconds, and 1,200 seconds. I don't think this is something you'd want to do in your head, and I probably wouldn't even enter it in my calculator all in one shot. What I would do is calculate the top and the bottom separately. So 750 plus 2,000 plus 1,000. So that's 3,750. On the bottom we have 360 plus 600 plus 1,200 plus 660. 360 plus 600 plus 1,200 plus 660 is 2,820. So if we take the distance of 3,750 and divide by the 2,820, I'm getting approximately 1.3 meters per second. And this is an average speed, which means it's a scalar, which means it does not have a direction. So this is approximately 1.3 meters per second. And that's how you find average speed. You would not get the right answer if you took the 4 speeds, calculated them separately, and then averaged them. It doesn't work that way because some of these intervals count for more because the time is greater. Let's take a look at part B, and then we're done with the examples here. What is the average velocity? Well, average velocity is going to be the total displacement over the time. If I go back and show you what I wrote for average speed, and there it is on the left-hand part of the screen, average speed is total distance over time. So all these numbers on the top were just distances. We can't do that anymore. We have to include direction for those numbers on the top. So for example, that 750 meters is east, the 2,000 meters is east, but the 1,000 meters is west. So what I might recommend here is you find the total displacement first. Just to back up for a second, this is distance, but as soon as I put that vector symbol over, we're talking displacement. So it's 750 meters east is positive, 2,000 meters east is positive, and then 1,000 meters west is negative, so I can put a negative 1,000 here, and I can add these up. I think that's 1,750. I'll check it with my calculator in a bit, but since I'm getting positive, that would mean the total displacement is to the west. I don't need to check that with my calculator. 2,000 minus 1,000 is 1,000, plus the 750 is 1,750. So what is the average velocity? It's positive 1,750 meters. The time is still, I think it was 28:20 seconds. Let's see what happens now. So 1,750 divided by the 28:20 gives me a measly 0.63 meters per second, and it's positive. So the average velocity, I forgot to write average here, I'll throw it in, is approximately positive 0.62 meters per second. That means, there's a way to explain what that means. I could just say, on average, that's how fast the person moved and the direction they moved in. But what I will tell you is that if the person exercising started here and finished here by doing all of those things, then they could still finish there had they started here and moved that way with this speed. It defeats the purpose of the exercise, but it's an equivalent displacement in that same period of time. Once again, particularly if you're at West Country Outreach School, you know that you certainly don't have to do all of these. What we want is for you to go through as many questions as you have time for and make sure that you understand the main ideas. So there are questions from your textbook, and I'm also recommending, if you have time, finish the assigned problems that are on pages 7 to 8 of the handout. In other words, the assigned problems that you haven't gotten to finish because you didn't have enough time earlier. Anyway, I hope that helps, and we'll see you soon. Take care.